Hello and welcome back. In section 2.6, we get to work with differentials and increments. So we'll start by just considering a basic polynomial function. We'll do f of x is x to the fourth power. If I'm looking to evaluate the value of the function at 3, f of 3, just a little substitution, and we get 3 to the fourth, 81. We're going to let delta x, there's a couple ways that you'll see this pronounced. This is either called the increment in x. More often you'll hear folks abbreviate it to just the name of the letter, delta x. So the idea here is how much are we changing x by? So here we're changing x by a positive 1/10 of a unit. In other words, our x was 3, now our x is 3 and 1/10. So we're just adding delta x to the previous x value. So that would be 3 and a 10th, 3 is to the fourth, 92 and 3,521 10,000ths. So delta y, the increment in y, not actually used to writing out the word delta. Every time I think the word delta, triangle comes out. Increment in y, delta y, saying, okay, how much did the y change by when the x changed by that much? So delta y for this case would be, we went up to a value of 92 and 3,521 10,000ths. We started at 81 on the money. So then delta y, how much the y changed by, 11 and 3,521 10,000ths. So if I look at the format, that should look pretty familiar to you. F of x plus delta x minus f of x all over delta x. That should look like our definition of the derivative. Well, up top, really this is just what we just found for delta y. We took the f of x plus the 1/10, so 3 plus a 10th, 3 and a 10th, and subtracted off what we got plugging in the original. So this is just the ratio of delta y to delta x. So 11 and 3,521 10,000ths to 1/10 is 113 and 521 hundredths. So I'm going to have you all do a little bit of work with increments. We're going to let g of x equal 1/3 of x cubed. And we're going to say x sub 1 is 2, and x sub 2 is 2 and 5/10. See if you can find delta x, how much the x is changed by. Delta y, g of x sub 1 plus delta x minus g of x sub 1 over delta x. And on this one, try a 4 decimal place approximation. In other words, the 10,000ths place. So go ahead and pause the video, give that a spin, and unpause it when you're done. Okay, so some things that we'll need to find what g of 2 is worth. So g of 2 is 8/3. If we're doing the approximation to the nearest, that's 100,000, 10,000ths, that'll be 2 and 6,667 10,000ths. G of 2 and 5/10ths, we get about 5 and 2,083 10,000ths. And that's all we need to find the rest of the puzzle. So delta x, how much did x change by? It rose by 1/2 a unit. In this case, x sub 2 minus x sub 1, you don't really need a formula for it. Change in x, how much did x change by? It went up by 1/2 of a unit. So change in y then would be the difference in these two guys. So our delta y lands us at 2 and 5,413 10,000ths. And the ratio of delta y to delta x we get 5 and 826 10,000ths. Again, rounding my answers to the nearest 10,000ths. So delta y over delta x, remember, is the same as this g of x sub 1 plus delta x minus g of x sub 1 over delta x. So now we're going to keep the same g of x as before. This time, x sub 1, we're going to keep it at 2. X sub 2, let's see if we can try this again with 2 and 1,000th. So see if you can find delta x, delta y, and the ratio of delta x, delta y. So go ahead and pause it. G of x is the same as before, 1/3 of x cubed. Okay, welcome back. So delta x, 2 and 1,000th minus 2 is 1,000th. We already have g of 2 and 1/1,000th. We get approximately 2.6707. Again, we're rounding. As a reminder from the other page, g of 2, 2.6667, 2 and 6,667 10,000ths. So our delta y is just the difference in those. So delta y, we end up at 4,000ths. And the ratio of delta y to delta x, 4,000ths to 1,000th, which it lands us on 4. So we're going to keep that number in the back of our minds here. So again, a pretty different value than we got for the last one. But we slid our x values much closer together. So here, delta x was 1/2 a unit wide. We went from 1/2 unit wide to to the x's being within 1/1000th of a unit of one another. So we slid the values much, much closer together. So the next thing we're going to do, and again, we're going to hang on to this g of x is a third of x cubed for a moment. This time we're going to find the derivative. So hopefully you remember some of the properties from 2.5. So g prime of x, hang on to whatever constants we already had. Exponent becomes a factor. Hang on to your base, drop 1 off of your exponent. So that becomes x squared. So one thing you might notice, g prime of 2 then is 2 squared, which is 4. So as delta x goes to 0, in other words, as we slide the two x values closer and closer to one another on the graph, so I start sliding the x values closer in, the ratio of delta y over delta x gets close to the value of g prime of x. So that's the idea with these increments. We slide the points in closer together. They start approximating the instantaneous rates of change. So next we'll look at the idea of differentials. So dy, the differential of y, dx, the differential of x. Not terribly surprising there. You might recognize those as being one of the ways that we wrote our derivative before. We used to write it a few times earlier in chapter 2 as dy over dx being the same as saying if f prime of x. Well, then that would lead us to the conclusion that if we want the value of dy, we would take f prime of x and multiply it by dx. Think of just isolating this dy, this differential, as if it were just a variable. You would just clear the fraction. All right, so to play with this, we'll look at f of x is, what did I pick? 3x squared plus 5x plus 1. Take a moment and find f prime of x. So go ahead and pause it, find f prime. Okay, welcome back. So hopefully you held on to your 3. 2 became a factor. X is now to the first power. Held on to the 5. X is now to the 0 power. Derivative of a constant is always a 0. And then just a little bit of cleanup. So then f prime of x would be 6x plus 5. X to the 0 is 1. 5 by 1 is just 5. So let's try some things with this. Let's play around with it a little bit. So we're going to find dy, the differential of y, for x is worth 1, dx is 1/10. So dy then would be 6 by 1 plus 5. So this is f prime of 1 times dx. dx is 1/10. Differential of x and increment of x have the same value. It's just saying how far apart the x's are. So dy, 11 by 1/10 1 and 1/10. Let's hang on to some of those same values, and I'll have you find dy for a new set of inputs. Okay, so the same f of x, same f prime of x as before. See if you can find dy. So if you flip the page already, f of x was 3x squared plus 5x plus 1, and f prime of x was 6x plus 5. So go ahead and pause that, see if you can find dy in these two scenarios. Okay, welcome back. So our first one, we'll find f prime of 2. So 6 by 2 plus 5. So 17. So then dy is 17 by 1/10, 1 and 7/10. F prime of -3. 6 by -3 plus 5. I don't know why I had an extra parenthesis there. -18 plus 5, -13. So then dy there, -13 by 1/100th is -13/100ths. Next, they have us work a few application problems. So we'll look at some cost revenue problems. So let's say we have some type of business, cost to make X units per week, C of X, 5,000 plus 2 times X, and our revenue for selling X units per week R is 10x minus x squared over 1,000. So we're going to use differentials to do a little bit of approximating. So that's one thing that is often done in business is we just use the models to estimate what's happening, and that should get us reasonably close rather than each time calculating exact values. So we're looking at how the revenue and profit will change if our sales go from 4,000, these are units, whatever it is we're selling, to 4,010 units per week. So R of x from our previous page, we had 10x minus 1/1000th of x squared. We will need our prime of x. So keep the 10, x to the first becomes x to the 0, which will drop it off, hang on to the negative 1/1000th. 2 is now a factor. X is now to the first power. And a little bit of simplifying, r prime of x then is 10 minus 1/500th of x. So the 2 and 1000, you just do a little bit of reducing there. So change in revenue with respect to change in units sold is r prime of x. So our change in revenue, we'll do r prime of x times dx. So our change in revenue under the given scenario, 4,000 to 4,010 units. We would do r prime of we would do r prime of 4,000. So our initial sales times the change in x. So times, in this case, 10. So r prime of x, 10 minus 4,000 over 500 times 10. So 10 minus 8, 2. 2 by 10 is 20. So dr is 20. So $20 per week is the approximate change in revenue. Now looking at profit, hopefully you recall profit is just revenue minus cost. So P of x here would be R of x minus C of x. So P of x, revenue from the previous page, was 10x minus 1/1000th of x squared, and we subtract off the cost, 5,000 plus 2x. So our profit function, P of x, negative 1/1000th of x squared. Let's see, we have a 10x and we have minus 2x, so plus 8x, and then minus 5,000. 5,000 would be sort of your fixed expenses on that. Okay, take a moment to find P prime of x and unpause it once you've got that all set. Okay, so P prime of x, welcome back, negative 1/1000th times 2x to the first plus 8x to the 0 plus 0. Derivative of any constant drops off, so P prime of x, negative 1/500th of x plus 8. So then change in profit will be approximated by P prime of 4,000 times 10. So P prime of 4,000, negative 1/500th by 4,000 plus 8 by 10. So let's see, so we have negative 8 plus 8. So 0 by 10 is 0. So dp 0 by 10, which is 0. So even though our revenue is increasing, our profit is staying approximately the same. changed by the way the 20 change would be an increase. So the profit will stay approximately the same. No change in profit. Okay, so in section 2.6, I would recommend 9 to 29 on the odds, 48 and 55. I'll also, as usual, try to upload the author's sort of generic 2.6 homework as well. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.